Hi class, so this video is to replace a demonstration that I used to do in class to do something instead as like a homework or a pre-class. And the purpose of this video and this demonstration is to show you how to use this relay module to control AC motors. Even though we're using components from the kits and these components aren't industrial grade, the principles are the same you can use for industry. So to start off, first thing we need is this relay module and an AC motor. And in this demonstration, I'm going to break up into two videos for two different motors. The first one is going to be this large single-phase AC motor. So let me show you real quick this motor, what it looks like. So here I have it on my table here. There's just a kind of a towel here to keep it from rattling, but this is an AC motor that I pulled out of a garage door opener, and can't throw anything away apparently. And then here's the capacitor that attaches to it and with the power wires. So we're going to control that here in a little bit, but let's talk about some specifications first. So here's the kind of the nameplate, the sticker that's on it that gives the specifications. So first off, you can see it's a 1/2 horsepower motor, 120 volts AC, 1500 RPM, which we can guess is, based on our synchronous speed calculation, is probably a 4-pole motor, because that would give a speed of 1800 RPM. So it's likely that the percent slip between 1500 and 1800 is, it's likely this is the speed, and so it would give a percent slip if it was a 4-pole of 17%. And I could take the motor apart, I guess, and figure it out for sure what poles it is, but I just haven't done that. Other things you can see on here, 5 amps, that's what it's rated to pull, 60 hertz, single phase, you see right here, single phase. It's curved, right? So I just took 2 pictures to see the curve. Meant for intermittent duty, so it's not really meant to run all day long. Service factor, what that means is a factor of 1.0. What that means, it's max output power is the rated power in horsepower, so 1/2 horsepower. If it had a service factor of 1.5, that means you can go 50% higher than it's rated just for a short, brief instant. So if it has a service factor of 1.5, that means you can go to like 3/4 horsepower, but this says just don't exceed it over 1/2 horsepower. This frame number is probably just something for the manufacturer. I don't recognize this frame number, 4ZY it looks like, but that's a common frame. It's common to list the frame so you know how to mount it. NEMA size motors have common frame numbers, but this doesn't appear to be one of those. Insulation class B, I don't know what this 5 is, but insulation class B, I got a picture, a little more details down here. If you have a service class or an insulation class B, that's what's saying its max operating temperature is 130 C or 266 Fahrenheit. What that means is just sitting in a room, it can't exceed that temperature. You're going to melt the insulation on the wires. It's not rated for a higher temperature. But also because of that, at a service factor of 1, you can't exceed 80 degrees Celsius increase in temperature. So whether it's in a really, really cold room or a room that's, at 50 degrees Celsius, don't go above a difference in temperature of 80, because just that temperature difference won't be able to cool itself. So that's what the insulation class does, is tells you just how insulated it is against, overheating and what temperature differences it can handle. This, I don't know what that is, a serial or something like that. Let's see, let's keep going. This capacitor, 58 microfarad capacitor at 250 volts AC is what it needs. If we look at the capacitor that's actually on it, I should have taken a picture of this, but it is, you see a little closer, it says 50 to 60 microfarad at 220 volts AC. So anyway, there's the capacitor. It is within the specs, so it needs at least that capacitor to be able to start. Rotation, it says rotate either direction. Thermally protected assembly in Mexico, Type C. Oh, a Type C motor. What that means is a NEMA Type C motor. Shows that you have pretty high starting torque. And then compared to a very common motor is a Class B, where it's a kind of low starting torque, but you have a peak torque. And then you see I have really high starting torque, and then it's pretty large relative percent slip. So if you're running at full load, right, the percent slip here is probably, if I go down, I should have drawn on this, but I don't know. 90 would be around here. So if this has a percent slip around 17%, then we'd be around here insulating at full load. So, but anyway, the point of Class C is just meant to have a higher starting torque. And because this motor came out of a garage door opener, right, it needs to move a heavy weight instantly. It doesn't have the time to build up its speed before you apply to load. So that's why it's good to have a Type C motor. So it has a really high starting torque. And then this is our wiring diagram. So I'm not sure what this red wire was ever for. I just kind of like tucked it away. But the black line needs to connect to the power. And then the other line, so I use the other power cord to connect to either the orange or yellow wire. And these two wires are connected on the capacitor. And if you can connect to one or the other, then it'll spin. I believe orange is counterclockwise and yellow is clockwise. And so you can see how a garage door opener could just use like a relay to switch between which ones are connected and be able to get the garage door to either raise or lower, just depending on how that's connected. To demonstrate using this motor, I'll demonstrate only spinning in one direction. In the next motor, I'll show you how to use the relay to spin in two directions. But something I'd like to show on this motor, I think the rest of this, loose a little bit, is just on the motor itself. So I'm just going to go to the full view here. Okay. So again, so here's the orange and yellow wires connected through a capacitor. So these two pins are connected to each other. Obviously, they're hard connected. And then these two are hard connected, but it has to go through the capacitor to connect these two. Okay. And so I can show you here first that the motor works. So I'm going to take, I took an AC power wire. Please don't do this at home. Put on some connections. We're not going to use the ground. The green is ground. The black is hot and the white is neutral. I'm going to connect hot to black here. And then to spin clockwise, we needed to connect it to yellow. So I'm going to hold this here and then just touch it, get it to spin. And you can see it spinning clockwise. And if I just touch it to the orange, now it's spinning counterclockwise. So, okay, the motor works. And again, all you have to do is connect. We have one side connected of, the AC line connected to the black wire. The other side, we just have to know which of the ends of the capacitor, depending on which direction you want it to turn. Now, one thing I want to show you is, what if we didn't have the capacitor? Remember, for single-phase motors, this is a single-phase motor, you need a capacitor, some way to start the motor to rotate. So this is a capacitor-run motor because it's never disconnected. And, well, I guess it could be in the controller, but when I wire it, I never disconnect it. But we need this capacitor in order to get to start rotating. And just to demonstrate that, I'm going to take out the capacitor. Because what's happening right now is when I connect power to one side, its primary winding is the orange line, and then the secondary winding through the capacitor is the yellow line, and the capacitor will phase shift that AC waveform by about 90 degrees and create a secondary winding in order to get it to rotate. And because the yellow wire, those coils are placed in a different location, it'll get it to spin counterclockwise because the orange is primary. If I reverse it and the yellow I connect directly to yellow, then the yellow is primary and the orange is the secondary, and because of its location, it'll get it to spin the opposite direction. What if I take out that secondary line? Okay, I could take out the capacitor altogether, but these are both, female-to-female connectors. I can't connect them, so I'm just going to use this connection point. But by taking out that line, I'm not using the capacitor at all. Okay, so I just want to show you what happens So again, if I power it, I don't know if you can hear it. You can see the spark, but it is drawing power, but it's not spinning. Now, I need a secondary wire just to get it to start spinning. I'm going to show you if I just spin it counterclockwise, just for a second, it'll keep going that direction. Okay, so it spun that direction counterclockwise. All I didn't do was nudge it. I can do the same in the opposite direction. If I just nudge it clockwise, it'll spin in that direction. So it spun clockwise. So the secondary winding is just to get it to move in one of the directions. It's not needed to stay on the whole time. But notice how it wouldn't run without giving it a nudge. So if this capacitor ever went out or went bad, the motor would still draw power, but wouldn't turn. All you'd have to do is just flick it in one direction or the other, and it would keep going in that direction. Okay. So I hope you can see that demonstrated here. So again, it works. That is counterclockwise, and then here is clockwise. So now what we want to do is disconnect this and now control it using our relay. So let me show the wiring diagram real quick. If I take our relay, this is just a little diagram of a DC motor, but the point is if I wanted to power this motor, I could just directly power it with positive or negative in either direction. The motor would spin either clockwise or counterclockwise. To control with a relay, all I have to do is take one of those wires and break the wire and connect it to the relay. And now the relay is controlling when those two wires are connected to allow power to flow through the motor. So this is what we're going to do with the relay. We're going to need to power the relay. Here's ground connection and 5 volts. And then I'm going to have a digital pin 2 connected to the Arduino to turn the relay on or off. Okay. By default, the relay is going to be connected to the normally open terminals. And so if this diagram is hard to see right here, so if you look up here in this diagram, the middle screw is what gets connected to either this point or this point, depending on whether this gets sent high or low. By default, if I send a high to digital pin 2, then the relay will stay in its normally open state. And then if I send low, it'll go to its normally closed state. So normally open is if I connect this pin to power, notice how this line right here is slanted down to this pin. And so this is the normally closed, and then this is the normally open. So these are not connected by default. And then these are connected by default. And so that's why I power to the middle pin and to this pin, because I don't want to have the relay be off or the Arduino disconnected and then have these points be normally connected to the motor just spinning by default. I'd rather have the wires interrupted or open by default. So that's why I wire it to these two terminals as shown up here. They're the normally open. So by default, if I send a high here, it'll keep it in this state. And then if I send it low, it'll switch this pin from, instead of being connected to these two together, it'll connect it to these two together. Okay. So let's go to that actual here. So here's the Arduino. Okay, so we have power going in to the common here. You see it says COM2 on this one, so this is COM1. And then this one right here is the normally open one. You can see up here it says normally open 2, normally closed 2. So this is normally closed 1, common, normally closed, normally open 1. So by connecting it to the motor to these two, the motor will not be powered by default. Okay, and then I have the VCC connected to 5 volts. The ground is connected to ground here, and then the in 1 is connected to digital pin 2. Okay, so if I take my AC power, which is still plugged in, I'm not going to use ground in this case. I'm going to keep my hot connected to black, and then I'm going to connect my neutral to common, and then I'm going to connect my my normally open to, let's just go counterclockwise, it's closest. In fact, maybe I'm just gonna lay this down. Okay, so everything is connected. Okay, nothing's spinning, it's powered on, but because the relay isn't powered or being activated by the Arduino, nothing's happening yet. Okay, so now what we're going to do, let's talk about the code. So the code, all I'm going to do is I set the relay pin to digital pin 2, I set it to an output, and I instantly turn it high because that's off on these relays. It's backwards than what we normally think, but high keeps the relay off. Then when I want to turn the motor on for 3 seconds, I make the relay pin go low. And what that does is connect power to flip the electromagnet in the relay to allow power, AC power to be connected to the motor. I'll have that for 3 seconds, and then I'll turn it off for 5 seconds. It'll spin down, and then it'll loop again. So for 3 seconds on, 5 seconds off, and then just repeat. And because I have it, and I've already uploaded this to the program, or to the Arduino, so I just need to connect it. But because I've connected to the orange wire, then the motor should spin counterclockwise. So here I'm going to take my cord to my computer, and all I have to do is plug it in, and it'll power the relay, and then run it for 3 seconds, then off for 5 seconds, and repeat. I'm going to hold on to it so it doesn't spin around. So there's 3 seconds on, and it's going to be off for 5 seconds, and then repeat. Okay, so you can see how simple that is to control a single-phase AC motor. You just need to be able to, one, it needs to be run. I'm going to disconnect power here before I hurt myself. I just need to take power, and here's the 2 lines, and I need to be able to connect it through the relay, and the relay will control when the power is being sent to the motor, and that's controlled through the program on the Arduino. Now, something to note here, on the bottom of this relay, all these pins are connected. I've disconnected power, but they're pretty exposed, and so if I connect AC power between these 2 lines, these are really close. If I set this down on anything metal, or if I, accidentally with my finger touch it and shorten those out, 1, the motor will run, and 2, it'll shock me. So you need to be careful with these relays when you connect them to AC power. The bottoms are really exposed. I recommend, screwing this down to a piece of wood or something using these screw holes, something that's non-conductive, or covering it with electric tape or something to protect yourself from shocking yourself or injuring yourself. Okay, I think that is it for this part of the demonstration. Yep, that's me just talking about don't touch it, don't short yourself out. So I'll stop the video here to get ready for part 2.